Hello, everyone. My name is Georgios Papadopoulos, and I'm an assistant professor at the Department of Information. Okay, so the subject of the presentation today is to show some computer vision technologies and how these are applied to the security domain. Let me continue. So this is the first use case of the project, where the goal is to collect in real time intelligence information regarding firearms incidents all around Europe and to exchange all this information among the different LEAs in the various member states. So the goal is to develop AI technologies in order to automate this process because this is a real-time big data problem. The second use case is a different, diverse one. Here, we are going to develop technologies to perform automatic and on-the-spot identification of the seized firearms. So imagine something like a mobile app that will take a picture of the incidents that happen in the physical space, and then they will try to identify the different characteristics of the various firearms, so the brand, the model, the caliber, because so far this process is not that easy, and the developed technologies will automatically populate the database of the practitioners, of the officers. The third use case has to do with the analysis of activities that happen online, and in particular in dark web marketplaces. Here, the biggest challenge has to do with the anonymity of the end user. Most of you should be familiar with this fact. I mean that everybody can upload on the web a lot of information, also illicit content, while hiding his real ID. So here the goal is to automatically detect and reveal which are the real identities of the individuals. And for doing that, apart from analyzing the content that is present in the marketplaces, we also analyze the cryptocurrency payments. So we deploy various blockchain technologies. The fourth use case has to do with incidents that involve the sending of firearms or components through regular post or carrier services. In this case, we employ scanning technologies like the ones that are usually placed in airports and travel agencies. So the goal is to analyze the very, very big amount of parcels that are sent on a daily basis so that to detect possible illicit devices or components in this content. And the last use case, also regarding online activities, one of the recent trends regarding firearms trafficking has to do with the development and distribution of blueprints. So figures that depict how to create your own firearm. Here, the scope of the project has to do with automatically detecting the blueprints of developing such 3D printed firearms and also to identify which are the criminals behind these activities. So this is what the project does, and now this is the overall functional architecture, which more or less summarizes what are the goals. On the left, you can see some operational aspects. So apart of the various technologies developed, we have to address issues like forensic aspects, legal aspects, how to exchange information among different organizations in different member states. So this is some critical operational aspects. In the heart of the system, as you can see, there is a wide set of AI technologies ranging from cyber patrolling tools to information fusion and big data analytics. On the upper part of the slide, you can see the tools that are and databases that are already available, and we need to connect with them. While in the bottom part, you can see the very wide range of data sources that we utilize for our analysis. Of course, in the end, as you can see on the right part of the slide, are in principle end users are police officers, border guards, or officers at the customs services. Now, let's see some more research aspects and in principle the activities that we are developing in Haracopin University with my team. The first one has to do with the analysis of visual content that we can find on the web. So this is a big data problem. So a lot of images that are distributed on a daily basis. And the goal is how to analyze all these images both efficiently and effectively. So the goal is to classify the images if they contain relevant content, so the presence of firearms, parts of firearms, or ammunition. Why we need that? Because this is critical for regarding concerns for public space security, collection of intelligence, and how to better speed up investigation procedures for law enforcement. As you can all understand, this is a big data problem, and we collect information from social media and dark web marketplaces. Regarding the technical aspects, we develop a deep neural network. So this is the type of AI we employ in this case. And two of the main families of neural networks that are currently the state of the art. So CNNs, the acronym for convolutional neural networks, and vision transformers, VIT. So currently, the dominant approach is in this type of analysis, the so-called transfer learning approach. So we assume that first we train the models in some large-scale database with generic images, for example, ImageNet, and then fine-tune the trained model in domain-specific data, the so-called downstream task. However, this approach is not always good enough and it requires lots and lots of data. So we have investigated the case of self-supervised learning. What is the difference? Before applying the fine-tuning step, we employ what we call a pretext task. So we let the machine to try to learn on its own. For example, comparing the upper with the bottom part of an image, and try to see what are the discriminant features for the domain of analysis. So as soon as we perform this unsupervised learning step, then we perform the actual fine-tuning on our application domain. There are many approaches that have been developed so far and are present in the literature. Here you can see four of the main ones that we have investigated. There are approaches that are based on contrasting learning, so comparing any relevant content. Approaches concerning some distillation learning mechanisms, how to transfer knowledge from one model to another. Masking, so putting black boxes on different images and then try to make the model to learn what is missing. And of course, clustering technique, so grouping the images in different semantic clusters, different groups of images, and then try to perform this prediction in real time. Here is the dataset that we have collected in Ceasefire. As you can see, we support 23 classes, semantic classes so far. Most of them are different types of firearms that we can see in images, for example, rifles, revolvers, rockets, shotguns, but also other types of objects that are usually present in suspicious images like bullets or box of bullets or other types of military clothing. Just to mention, this dataset has been collected through manual effort, so some of the officers have provided us with exemplary images. This is the part that is absolutely necessary for developing the AI module. And here are some experimental results. On the upper part are the results for the various self-supervised learning technologies, and the first line is the benchmark, the baseline. So what is the results achieved without using self-supervising? As you can see, for both types of neural networks, both VIT and ResNet, self-supervised learning includes inserts a significant improvement in the detection performance. Here is the confusion matrix. So ideally, we want uh, the percentages, the correct predictions in the main direction to receive high values. So you can see that our algorithm performs quite well for most of the defined concepts. Also, an additional experimental setup where we used another offline database of forums that has been provided in the pretext task from the end users of the project, and we again implemented the self-supervised learning paradigm, where again, as you can see, the first line is the benchmark, and the bold line is the one that we have developed, and we observe in most of the cases a significant improvement in performance. So this is the first type of technology that we have developed regarding regular image analysis. And now the second one that is connected with another use case of the project. Here we analyze X-ray images as we obtain it from scanners, for example, from different types of parsers. And here the goal is to try to, in automatic way, to detect suspicious objects, so different types of guns or ammunition. So again, why this problem is important? Imagine that we have a lot of X-ray scanning devices placed in airports or post offices. There is a very, very large volume of parcels that need to investigate it on a daily basis. So in principle, so far, this process is performed in a manual way, and this is not always efficient, and it's always hard for the various practitioners to perform it. So this is essentially, again, a big data problem, and we are investigating different types of technologies to automatize this procedure and also in a reliable way. So what we develop in this context is a different set of object detection modules in order to identify different types of, let's say, explosive weapons or sharp objects, everything that could cause harm. There are a lot of challenges in this case. For example, there are a lot of objects that are occluded. Imagine that when the X-ray penetrates a parcel or baggage, usually one object is depicted on top of others. So it's not really easy to distinguish the different objects. Also, the scene, the visual environment may contain a lot of clutter, so a lot of objects that are placed together. So it's not very easy to identify the boundaries of the object. Additional class problems are that different types of materials have different reflections to the X-rays, and also the positive samples, so this potential danger, are not always easy to find. So it's not really easy to train a module to perform this task. There are different types of algorithms presented so far. So there are the so-called anchor-based detectors. So we try to specify first where in the image an object of interest may be present. So usually this is a time-consuming process, but quite precise. There are anchor-free detectors. So this aim to classify the different pixels of the image if they belong to a different type of object. And also there is a category called single stage that performs both the previous two steps. It's very fast, but not always as accurate as the first one. So we try to investigate different types of technologies belonging to these three main categories. So we have actually implemented a comparative evaluation assessment with different types of AI technology. So again, deep neural networks. And we have employed a public dataset for this, the so-called sixth-ray dataset that contains scanned images of different types of luggage, as you can see on the right part of the slide. And we try to evaluate which method exhibits the best recognition performance. Here are some samples of the employed dataset. So you can see there are 7 different categories. We try to identify different types of guns, knives, pliers, scissors, etc. Each luggage in these experimental settings contains only one type of illicit item, and we have experimented with the setup provided in this public benchmark. Here are some of the evaluation results. On the left, you can see different types of technologies, so different types of neural networks. I will not go into many details, but you can see that the Dino method that actually performs some kind of knowledge distillation performs the best, so something like around a 90% recognition rate. And on the right part of the slide, you can see some of these correct detections. For example, you can see that we have identified correctly the presence of a knife with a percentage up to 90% confidence, or different type of guns. As you can see, this concerns some fine-grained analysis of the images, so very small ones and with small differences among different instances. And this was the presentation, and thank you for your time. I'm at your availability for any possible questions.